Okay, so starting our new packet, there are two things that we're going to be learning in this. Okay, so our semester now is going to be focused on this thing called inference. So just in general, what does it mean if you were going to infer something? Okay, good. You're going to be taking a guess about something else. So that's what we're doing in this first chapter 19. We're going to get a sample, and from that sample, we're going to take a guess or make an estimate about something that we don't know. All right, so that's how we do that. So, again, inference is knowing that you just have a sample. We want to know what we can infer about the entire population. Okay? So there are two kinds of inference. And our chapter 19 is going to focus on these confidence intervals, and that would be something like this. We want to know a parameter. And a parameter is something about the population. For example, if I want to know the average length of a rattlesnake, of all rattlesnakes, okay, if I want to know the average length, do I need to go and measure them all? No, heck no. So I would take a representative sample and from that make an estimate of for what's for the population. All right. Then, when we get into chapter 20, so by the way, this was chapter 19, which we're going to start today. Then, when we get into the other part of this packet, chapter 20, we will compare items to a claim. One way we could do it is say we compare, we wonder, is Michael Jackson more popular than Princess Di? And so we could compare those and we make a yes-no claim as to their popularity is the same, or one's more popular, or one's less popular, whatever. Okay, so let's first deal with our confidence intervals. We also are going to put means to rest for a while. So for the next 4 chapters, we will be dealing with categorical data, which is dealing with just proportions. Okay? Dealing with just proportions. All right. Okay. So here we go. If we really don't know the population characteristic, we don't know the true proportion of people that have blue eyes or whatever, and we want to know that, then we will get a confidence interval, and that is a range of plausible values. A range of plausible values that we hope that within our possible values, we have captured the real answer. So we hope that within our sample range, we've got the true proportion, the realistic answer of the proportion of the population that has blue eyes or whatever. Okay, so at least we can get a ballpark idea. So we're going to collect some data today. And what we are going to be estimating, we are going to make an estimate for this, the true proportion of water on the globe. So I have these little toy globes that I've blown up. They're like little beach balls. And so we're going to estimate the true proportion of water on those globes. So the way we're going to do this, because you need to be fairly accurate, your finger is too big of a surface area when you throw these globes. So you need to take a pin and make a pinpoint on your finger like this. So borrow somebody's pen if you don't have a pen, and make a pinpoint. So I have a pinpoint now on the tip of my index finger. Okay? Listen up. Once you have a pinpoint on your index finger, then you will be in a group of 2 or 3. If you're in a group of 3, then you'll have one person to collect the data and 2 people to throw the globe between. If you're in a group of 2, then y'all will just throw it back and forth between each other, and then somebody will have to keep track of the data. So groups of 2 or 3. I want you will throw the globe 50 times. When you toss that globe, you want to throw it in the air and kind of twist it around. Why is it important to twist it around? So you are randomizing it. Very good. So we want to twist it around so that we randomize it, and then you will record, landed on water, landed on water, landed on water, landed on land. landed on land, landed on water, and so on. And keep track. You need to kind of count every so often because you need the total of all of those, of all of it together, to be 50. So once you have reached your 50th piece of data, stop. And then once you have reached your 50th piece of data, come up with your number of items, and then you will make your proportion, which would be like 33 out of 50 or whatever it is that your data is. And so for me, that was 66%. Okay? All right, so we're going to collect some data. You decide who you're with. I'll get you your globes, and go ahead and start collecting your data. Okay, I just wanted to put on the video that I had forgotten to tell you guys that, again, I know y'all did this while you were working. The North Pole is ice, so that counts as your water, and then your South Pole has land underneath the ice, so that one counted as land, okay? So now you have gotten your total of your sample over your 50. This is your group's p hat, because that is your sample proportion, okay? Your sample proportion. Okay, that is also, because it is made from a sample, is called a statistic. Because it is made from a sample, is called a statistic. It is your sample proportion. And that is important because when we go on to the next page and we look at the formula of how you mathematically compute a confidence interval, the very first thing in your interval, it is built off of your sample proportion. So your p hat will be the center of your group's interval. We will be making an interval that will look something like this. You'll have your p hat value, and then you will get a margin of error up, and then a margin of error down. And so this makes this range of data from a low value to a high value that you are hoping that this range of values captures the real answer, the true proportion of water that is on the globe, okay? So let's kind of talk through these formulas here. So the formula is the statistic plus or minus. This plus or minus goes into making the plus to get the top whisker and the minus to get the bottom whisker. Okay, so that is going to make the upper and lower whiskers. Okay, not truly like box plot whiskers. They're not like the exact same. No, these are not to be confused with the quartiles of a box plot whisker, okay? All right, now this critical value is written and notated with a Z star. It is like a Z score, but it's just a teensy, we think of it kind of in a backwards way. This number is based on how confident you are supposed to be. Your confidence level. For example, you may be asked, create a 95% confidence interval. That means you are 95% confident that you captured the true proportion of water on the globe. Okay, so we all are going to make a 95% confidence interval today. The reason you don't make a 100% one is because the more confident you are, the bigger the interval has to be, because you have to be more confident that you actually captured it. So a 100% confidence interval would go from negative infinity to positive infinity, because you have to be 100% confident that you captured the true answer. So that doesn't really work out too well. All right, so that's from your confidence level. Now, look at this standard deviation. We know that is that standard deviation of our p hats, and we remember. Do you remember the formula for that we have recently done? That's that square root. 1 minus p, over n. Very good. Okay? All right. So before we actually construct that, we need to understand what this thing called critical value is, okay? Let's focus on this critical value right here. So here we go. We need to know how to compute that. So the critical value has to do with z-scores. Okay, it's related because it tells us how many of our samples standard deviations that we are away from our statistic. Okay, what do you, tell me just in general what a standard deviation is telling you. If I say your standard deviation, if your z-score is 1.5, what does that mean? Yes. Perfect. You're 1.5 standard deviations away from the mean or whatever. Okay, this is the same kind of thing. It's just that we have to use our samples standard deviations, and it's how far we are away from our own our own p hat. Okay, not mean. All right, so common confidence levels that we are asked to do is 90%, 95%, 99%, and so let's talk about how to get the number value that goes with that. And so let's take a look here. Let's see. Let's go through this process and let me teach you how to get it. So here's an example of 90% confidence right here. If you want to be 90% confident, then you have 90% of data centered around your p hat. So this is 90% of data here in the center, okay? So what I need to do is figure out how many standard deviations do I go up and how many standard deviations do I go down so that 90% of the data is in the center. All right? Okay, so that's the first thing. 90% is in the center if I'm 90% confident. So let me ask you this. If 90% is in the center, how much is left in the tails? 10 total, which puts how much in each one? Okay, good. So that puts 5% here and 5% here. So now, I want to identify the z-score right there. And we're going to call it a z-star because it's going to be based off of, because we're kind of going backwards off of confidence level. So how do I get that location right there that has 5% below it? Of the? Yes, excellent. Okay, good. So that is inverse norm of the area below is the z at that spot. Perfect. Y'all did a good job on that. Okay, good. So inverse norm of that area below. So in my calculator, I will compute inverse norm of 0.05. Okay, and I'm going to go ahead and tell you what that gives you. That gives you the number negative 1.64. Okay, so it gives you the negative version. What do you think that this z-score is right up here? It's the positive version. They are, because of symmetry, one of them is the negative and one of them is the positive. Now, whenever we're going to write our, whenever we're going to do our computing in a moment, I'm just going to use the positive version. You know why? Yeah, this thing, good job. This thing right here accounts for one of them being positive and one of them being negative. So just use the number. Just use that magnitude and just think one of them is the positive version and one of them is the negative, and that's accounted for in the formula already. Okay, so keep it on going. Let's practice some on our own. So I have these, for example, 95% confidence. I have some little normal models over here for you. So if I say be 95% confident, what does that put in the center? Okay, good. So draw yourself some this and put 95% in the center. Okay. If you have 95% in the center, how much is left? 2.5 in both tails. That's 2.5% in both tails. Well, I need that to be a decimal. What is that as a decimal? Okay, so the z-star for this is inverse norm of 0.025. And I'll go ahead and tell you that answer because I know you could do that in your calculator. That's under second vars. Second vars, by the way. Okay, is 1.96. Okay. Now, notice I I want to make this a quick connection here. Do you see this number was 1.64 and this number was 1.96? So as I am more confident. Well, it will give you negative, but like I said, you can use, yes, it'll count for both. So, hey, listen up, guys. If 90% confidence gives me this number 1.64, and 95% confidence is giving me this number 1.96, do you notice as I get more confident, what happens to the size of my z-star? It's getting bigger. So more confidence is making it a bigger Z star, which ends up making it bigger whiskers, longer whiskers. See, that's why. Hmm? That means that, yeah, it's like a bigger interval, and so you kind of are not being as accurate, yeah. Because you have to be 95% confident that you captured the real answer now. Let's do another one. Why don't you try? I'm going to take a moment. Let you do the 80% confidence and the 88% confidence. Do that now. Question. Okay, so again, when you do those, you will get the negative number. But just use the value of it because, yeah, just go ahead and put down the positive version of it because the formula will take care of the plus and the minus. Okay, very good. So that is your critical value. That has to do with how confident you're going to be. Next. So the next thing is in the formula. So we've gone through the formula. We got this statistic was the p hat. This critical value was our z star. Plus minus, and now you pretty much know how to do this standard deviation. There's just one little catch to it. So let's talk about this. You know that that is the square root of p, 1 minus p over n. So here's my question to you. Let's try to compute this for our globe. So tell me what is the true p for our globe. Tell me what's the true p for our globe. I need to put this number in here. What's the true p? What? Do you know what proportion of water is on this globe? Is that not what we are estimating to begin with? Isn't that what we are trying to figure out? So, yeah, hey, we do not actually know the true P. And so, if you did, true P is the best it can be, and you want to use that. But since we don't have that, we use the best thing we have, which is P hat. See? True P is the best it can be, but if you don't have that, you're going to use P hat. Okay? I did make a little song out of it, yes, but we're not going to listen to it because it has something to do with something else. So true P is the best it can be, but if you don't have that, you're going to use P hat. And so then when you get your own data, then that's how we're going to do that. So let's use my data. My data. Everybody practice with me once, and then you're going to do your own. So my P hat that I used, I got 33 over 50, so mine was 0.66. So here we go. Let's do this. What is my statistic? Yeah, use my information right now. Everybody do the same. What's my information? Nope, my statistic is my P hat. Yeah, this is my P hat. That's my 0.66. Okay? Plus or minus. Critical value, that has to do with how confident. And I want us all to make 95% confidence intervals. So what is the Z star for 95% confidence? Yeah, if you look at the previous page, we did it already, and it was 1.96. So there's my 1.96. Okay? Now, let me figure out my standard deviation. I got to do this 0.66 times the other part, 0.34, over what's n. For every single person in here, we all had 50 as our n. Okay? So I've already computed that. They are about to be multiplied. Yes, the 1.96 is about to be multiplied. This standard deviation, by the way, is, so let me tell you what it came out to be, 1.96. This came out to be 0.067. Okay? Now, let's not let the order of operations screw us up. Of this little thing written right here, what has to get done first? This multiplication has to be done first. And 1.96 times 0.067 is 0.13. So I will be making my interval from 0.66 plus 0.13. That will give me my upper part of my interval. And then 0.66 minus. So we will end up our answer like an ordered pair. Set notation. So let me demonstrate here. This number is going to come from 0.66 minus 0.13. Okay? And that number is, of course, 0.53. where do you think this number is going to come from? Good. 0.66 plus 0.13. Okay? And that is 0.79. So I am 95% confident that the true proportion of water on the globe is between 53% and 79%. Question? Yes, you want to write it in smaller to bigger, so you definitely want to put the smaller number first. Now, that's my interval. That is my personal interval. Now, let me tell you something real quick, because after you get your interval, we're going to put them on the board, okay? That means that my p hat was 0.66 and my upper bound was 0.79 and my lower bound was 0.53. Now, by the way, this distance here was my margin of error. How big was my margin of error? Yes, 0.13. Good. Because I went 0.13 up and I went 0.13 down. My margin of error went 0.13 up and 0.13 down. So it's symmetrical. Okay? All right. So let me go ahead and stop and let you and your people in your group practice computing your own interval based off of your personal p hat that you just got. Okay? Everybody make your own interval right now. Okay, so when you got your interval, again, it should have the lower number first, comma, the higher number second. And then I got a question, do I want you to draw a picture? Yes, I want you to. So everybody, listen up. I want you to, somewhere, I don't care where, put your picture. I want you to know that this point in the center is your p hat. And then you go up your margin of error and put your high value. That's your high number. And then go down here. This is your low number. And then furthermore, this right here, that's an important thing. That is called your margin of error. So we're going to abbreviate that ME. And we'll talk more about that when we do the second notes. ME stands for that margin of error. So that's your margin of error up, and then you have the margin of error down. So I want you to put your numbers in, because I'm about to have you, in fact, we may do this first thing tomorrow, or while you guys are working. We're going to, as you can see over there on the sideboard, do you see all those other confidence intervals from my other classes that did this data? We're going to add our data to that and put our confidence intervals on the board as well. So we'll actually add those tomorrow. So the last thing I want us to do now, okay, listen up. The last thing I want us to do is write a conclusion sentence. So here it goes. I am 95% confident that the true proportion of water on the globe, because that's what we're figuring, that's what we are estimating. The true proportion of water on the globe is between, and then you put your two numbers, blank percent and blank percent. Okay, that's your conclusion in context. I am 95% confident that the true proportion of water on the globe is between blank and blank. I'm letting us go ahead and round to whole numbers on these. Let's just do that. Simplify rounding to whole numbers. Let's keep it simple. All right, so hey, quick summary. Quick summary. What does a confidence interval do for us? No. Hey, everybody stop. Quit moving. Have a seat. Listen up. What does a confidence interval gave us those numbers from the low one to the high one. What are we hoping to do with those sets of numbers?
Find the true.
Thank you. We're hoping that it captured the true proportion, an estimate of the true proportion. Very good. We will do some more of that computing tomorrow. Good deal.